We learned about vectors a while ago, and we learned about vector notation, we learned about unit vectors, we learned about how to add vectors and how to subtract them, and how to find their magnitude and how to find their angle. But we did a lot of different type of math operations with vectors, except multiplication. We didn't talk about how to multiply vectors or when to multiply vectors or what it means. And there are two ways to multiply vectors. We're going to only learn one of them this semester. Next semester we'll learn the other one. This is the easier of the two. And it is called the scalar product. But more often you're going to hear it called the dot product. Which is kind of a silly thing, but that's the way we refer to it fondly, I guess. The reason it's called the scalar product is because you're taking two vectors and you're performing a multiplication operation on them, and what you get out is a scalar. Okay, so the thing that you get after you multiply two vectors together is not a vector anymore. You de-vectorized it. So what does it mean? What does it mean, and how do we represent it with notation? If you have two vectors, vector A and vector B, the way we write down the dot product is with a big dot. A dot B. These two vectors dotted together gives you some sort of scalar value. Okay, what it gives you is a number, just a number. All of the unit vector notation is completely gone. And what it means is it's the magnitude of the two vectors multiplied together, but only the components that are in the same direction as one another. So if I have, for example, like vector A is pointing off in some random direction, and then vector B is pointing off in some other random direction, then what I want, and we'll talk about why I want this later, what I want is the component of vector A that's in the same direction as vector B times vector B. Because all I want from this vector A is the part of it that is doing something in the same direction as vector B. Okay, and I'm not trying to be abstract on purpose. The purpose of learning about this is to do work. Okay, the concept of work has to do with a force causing a displacement. And the only part of a force that actually does work on something is the part of the force that's in the same direction as the displacement. Okay, so that's why we end up wanting to use the dot product in this class. The dot product comes up in other things, in other parts of physics, but in this class, the only time really ever you're going to use the dot product is when you're talking about work. Okay, but for today, I want it to be more generic, where we're just trying to take two vectors and take the dot product of those two vectors. Now, it's not just for the purpose of saying, I want the component of vector A that's in the direction of vector B, and I want to multiply those two things together. The other thing that's really useful when you're using a dot product is to find the angle between two vectors really easily. Okay, to find the angle theta that is represented by the angle between the two vectors. Okay, so there are two ways to take the dot product. Two. The first way is to take the magnitude of vector A times the magnitude of vector B times cosine of the angle between the two of them. So theta is measured between the direction of vector A and the direction of vector B. So for example, if I draw a little coordinate system at these two vectors at their tails, let's say vector B is at 30 degrees and vector A is at 70 degrees, then theta becomes 40 degrees. Okay, it's the angle between these two vectors. But this is a magnitude and this is a magnitude. The other way to take a dot product is to take the components of the vectors, multiply them together, and then add them together. For example, let's say instead of writing vector A as some magnitude with some angle, we say that vector A is equal to A x hat plus A y hat plus A z hat. Right? This is the other way that we write vectors in terms of the unit vectors. Right? You don't always see the z hats, but in this case we might as well do it as generically as possible. Vector B, let's call bx x hat plus by y hat plus bz z hat. Generically. We'll do it with numbers in a little bit. So one way to find the dot product is to use AB cosine theta. But in this case, it's weird, it's difficult to do that because you don't know what the angle of this vector is. You don't know what the angle between them is. So it's difficult for you to use this form of the dot product. In fact, it's probably impossible. That's silly. It's not impossible. It's not easy to do. So the other way to take the dot product, like I said, the other way would be to multiply the components together. And what I mean by that is you take the x components and you multiply them together. So ax, bx. And then plus the y components multiplied together, ay, by. Plus the z components multiplied together, a, z, b, z. So, let's do an example. Let's say that vector A is equal to 3x hat minus 4y hat plus 7z hat. And vector B is equal to negative 2x hat plus y hat plus 2z hat. Question number 1. What is the dot product of those two vectors? What is A dotted with B? How would you do it? First of all, you wouldn't just get out your calculator and start typing numbers into it because we are doing the very first dot product you've ever done, right? And in your notes, what you want is to be able to look back and see what you did. So let's write out all of the steps. So we have these in vector notation, right? Unit vector notation. So it's going to be the x components multiplied together, so 3 times negative 2, plus the y components multiplied together, negative 4 times what? 1, plus the z components multiplied together, 7 times 2. So, the dot product, or the scalar product, A dotted with B, gives me 4. It's not 4x hat, it's just 4. It's a scalar. It doesn't have direction anymore. It's lost that. Okay? It's lost that. Okay. Next question. Vector A is equal to 3x hat, and vector B is equal to 2y hat. What is the dot product? 0. Why?
Because since there's no x, there's no b of x, it just is 0, so 3 times 0 is 0, and 2 times 0 is 0.
There's no shared vectors.
There's no shared components, right? So there are lots of different ways to think about it. First of all, we could say 3x hat plus 0y hat, and then we could say this is 0x hat plus 2y hat, right? So 3 times 0 plus 0 times 2 is 0. The other way to think about it is that the angle between these two vectors, 3x hat and 2y hat, is what? Exactly 90 degrees. Things that are perpendicular, vectors that are perpendicular to one another, have a dot product of 0 because cosine of 90 degrees is 0. And the other way to think about it is that there is no component of vector A that is in the direction of vector B. If they're absolutely perpendicular to one another, then there is no component of one that's along the other one. That's the definition of perpendicular. In fact, that's one way for you to find another vector that's perpendicular to a vector that you've already been given. For example, what if I say, find a vector that is perpendicular to vector A. There's not just one answer.
0.
No, well, that's not a vector. Okay, see, so there's not just one answer. You're right, you guys, quit it. Yes, z hat is always going to be perpendicular to anything that's in the xy plane. Find me something in the xy plane that's perpendicular. When I say something that's perpendicular, what I mean is it is at a 90-degree angle with respect to this vector, right? So what that means is that the dot product between these two things has to give me what value? 0. Which means I'm going to take 3 times something plus negative 2 times something, and I'm going to get 0. There are like 8 billion different ways to do it, right? The easiest way to do it is to switch the values, right? Switch your x's and your y's. So negative 2x hat plus 3y hat, magically, 3 times negative 2, negative 2 times 3. Those two things are, oh, whoops, switch them, and then you have to switch the sign of one of them also. That's my fault, sorry. Because 3 times 2 is 6, and then negative 2 times 3 is negative 6, so then that gives you a 0 dot product. That's not the only answer, right? Because the magnitude of this vector can change completely. It's really just the direction that matters. So I can scale this number up or down, but the slope of it, and the other way to think about this is the slope of this vector, this line represented by this vector, is rise over run negative 2/3. If you recall, you've had to come up with in your lifetime an equation of a line that is perpendicular to another line. And the way that you did that was you flipped the slope and then you changed the sign of it, right? This slope is rise over run 3/2. Same thing, because slope just tells you the direction of a line. Yeah?
Doesn't matter which one you change. Like,
You tell me.
The sign.
You tell me. Do it the other way. See what happens. No. So if we switch them, and I make instead this one negative, and leave that one negative, then I get a plus and a minus, but they're still the same magnitude, and so they cancel out. Yeah. Okay. Because these two vectors, the two that we just talked about, positive 2x hat and 3y hat, or negative 2x hat and negative 3y hat, are those two vectors, right? They're on the same line. They have the same rise over run, the same slope. Okay, so this is like algebra 2 combined with vector calculus. So like 11th, 10th grade math and 3rd semester calculus. Okay. Huh?
Good afternoon, Lancers. Here's
What?
your afternoon announcements.
All
Take
right.
your friends' word for it. Read the book 13 Reasons Why by Kate Atkinson.
Luckily, you've got enough to do your homework.
Next.